Okay, hello. Apologies for the kind of strange nature of this. I'm just recording this one in a impromptu studio in the hospital. Let's see, does that work? There we go. So the question was, what the heck's a conservative force, and how does that work? How does that actually conserve energy? How's the total energy conserved? And also, what the heck is path independence, right? So I'm going to try and re-explain what a conservative force is. And to start with, you have to understand that every conservative force, so all conservative forces, right, have, and they must have, an associated potential energy, right? Because a conservative force is one that can give energy to and take energy away from the potential energy of an object. For example, there is gravity, right? And gravity has gravitational potential energy. Only the force of gravity, or kind of whenever the gravitational potential energy of something changes, the work done by gravity or the force due to gravity is involved. The same thing could be said of a spring. A spring can exert a force, and there can be a spring potential energy, or a magnetic potential energy from a magnetic force, or an electric potential energy from an electric force. But every single conservative force is by definition one that has a potential energy, okay? Now for physics, there are only 4 of these, okay? It's gravity, or a spring, or electricity, or magnetism. Those are the 4, there we go. Those are the 4 conservative forces so far as you are concerned. Now, you can make arguments as to there being others, but for the course that you're doing, and especially for my section, it's actually going to be a spring and gravity, but that's it. Right? So if it's gravity, it's a conservative force. If it's a spring, it's a conservative force. Everything else is non-conservative. Now, what we mean by conservative is that it draws upon or adds to potential energy. Let's use gravity as an example, right? Like you could have an object, right? Now, an object has a position in a gravitational field. Let's say it's got a height, right? And let's say that if we were to record its potential energy and its kinetic energy, right? The potential energy would be high, and the kinetic energy would be nothing, right? And then if you let gravity do work on this object, right, then as it falls down, the potential energy becomes 0, but the kinetic energy becomes some, right? And in fact, this kinetic energy is equal to this potential energy. So in this case, the potential energy was converted to kinetic energy, but that can only be done by the force to which that potential energy is associated, right? So the potential energy can be converted to kinetic energy only via gravity, right? Only by the force due to gravity. Now that said, right, this kinetic energy can be altered by any work, right? So it's entirely possible for someone to say, catch this ball, right, and leave it in a third state where the object is at the bottom, but it is also at a velocity of 0. So this was some sort of fast velocity, and this was some velocity equals 0, right? It's possible for the object to be at the bottom, and here it will have a kinetic energy of nothing and a potential energy of nothing. Now the idea is that under gravity, right, the potential energy and the kinetic energy are always going to add up to be the same number. So anytime the object gains in kinetic energy because of gravity, it will lose potential energy, and vice versa. Anytime the object loses kinetic energy because of gravity, it must correspondingly gain that much potential energy, that much gravitational potential energy. So conservative force is one for which there is this exchange. So energy lost in one form is gained in another. And that only happens, that exchange always happens, or at least for us, between kinetic energy and some form of potential energy. For springs, which you'll see in tomorrow's lecture, it's going to be an exchange between the kinetic energy of the spring, or the kinetic energy of the mass on the spring, and the potential energy of the spring, which is another formula, right? So that means that a conservative force, well, for you, it's gravity, or a spring, or electric force, or magnetic force. And it is the thing that allows potential energy to be accessed, right? And it can either drain the potential energy to convert it to kinetic energy, which is what happens when you let it go, basically, right? Like, that's what happens naturally, right? The potential energy, if you drop something, right, it always falls down. So the potential energy always converts to kinetic. But it can, if you throw it up, right? So that's initially perturbing the system, then the kinetic energy will be down, will decrease, and the potential energy will increase. So that's a conservative system, okay? It's one that, or a conservative force, is one that can access or exchange energy between potential and kinetic. Now for us, we're talking about gravitational potential energy. So we're talking about gravitational force and gravitational potential energy. Every other force is non-conservative. Every other force changes the total energy state, all right? Gravitational force exchanges between gravitational potential energy and kinetic energy, and it can be an exchange where it adds, so like we lose potential, we gain kinetic, or it can be an exchange where we lose potential and gain kinetic. I pretend I said it the right way. But the total is always the same when the conservative force alone is acting. And if you want to change the total, either increase it or decrease it, you need to do non-conservative work or work by a non-conservative force. And that can change the total. Now, technically, the non-conservative force should only be changing the kinetic energy, but it's a bit complicated. So don't worry about like what changes what too much. Just say that the potential energy can only really be accessed by a conservative force. And the conservative force is called conservative because it conserves the total amount. It exchanges energy between one of these two types, and then any other force can actually just remove energy or add energy to it. Now let's talk about another thing called path independence, all right? So let's imagine you have two heights, one here and one here, right? And you have a brick, okay? Now, if I were to take this brick and bring it up here, right, it would gain a total potential energy, delta U, of mg delta h, right? Which means the work done by gravity must be mg delta h, right? That's kind of by definition, right? The work done by our conservative force must be equal to the change in potential energy that's associated with that conservative force, but also, right, it has a height difference of h. Let's say this is delta h, so that's the total height difference. So that's the total potential energy difference. Now what if I took this object and I moved it here, and then I moved it here, right? And let's say, the initial and final velocities are the same. Now, you might be able to argue that more work was done here, you might not. But what you cannot argue is that the potential energy change, delta U, is still mg delta h, because the potential energy doesn't care about these sideways motions. This is what we mean by path independence. The difference in potential energy between state 1 and state 2 is independent of the path taken to get from state 1 to state 2. So you just go from here to there, or do some sort of squiggle to get to state 2. It doesn't matter. All that matters is the difference between the two paths. Now, this happens for a lot of different potentials. For example, in an electric field, which you haven't learned yet, but in an electric field, and you have an electrical charge or something, as it moves around, right, all we really care about is how far it moves along the electric field direction. We don't really care about the horizontal motion. And so the electric potential energy of this electron would be said to be path independent because it depends only on the start state and the end state, and the interims doesn't matter. In fact, you could even, right, imagine a particle that went up and down, right? If V equals 0 in both cases, right? So we're only talking about the change in potential energy, then it's still the same, right? Our start point is here, our end point is here. It doesn't matter that we did this extra motion because the total change in potential energy is still the final minus the initial. That's what path independence means, right? And I guess the notion that a conservative force has path independence essentially means that a conservative force is associated with a potential energy, because potential energies are path independent, right? The potential energy only cares about where you were in the field and where you are in the field, and not how fast you were going to get there or what work needed to be done to get there or where you went or whatever. So that's path independence. Okay, I hope that was useful. Let me know if not. I understand it's a bit kind of weird looking, but this is the best I could do. So see you in the lecture tomorrow, and have a good day.